So I'm Reza Rasoulpour, and I have the opportunity, there you go, to provide an overview, a conclusion. What did we hear over the past 28 hours? And what does it mean, and where do we go from here? So I'm really looking forward to that. I gave this a lot of thought, and one of the things that I've learned is that we have an opportunity for intervention. And actually, the intervention component of this is really exciting. So I'm going to do a little bit of intervention on this title slide, because you may notice that environmental is spelled wrong. So what I've learned is that I can use gene editing techniques to do an intervention and change that to environmental. Of course, I have an off-target effect right here, and that became preemptive. All right, so in all seriousness, where we were 28 hours ago. So Lisa set forth the goals of this workshop. And the goals of this workshop were, I think, really, really exciting. This is a new area of science. It's rapidly evolving, and we hear about it all over the place. So what does it mean? Let's raise some awareness about it, and let's broaden our understanding and familiarity of it from an environmental health perspective, then spark ideas on how these tools can be used in ways that we weren't using them before. So let's go over the past day and a half and see if we've actually accomplished that. And I'd actually like to start with a slide that Dr. Ernov showed, which was the rhinoceros. And I think a lot of people had different perspectives about this rhinoceros when it came up. So this was a rhinoceros picture from the 16th century by someone who had never seen a rhinoceros before. And Dr. Ernov was talking about the fact that there's an extra horn here, and there's scales, and there's all this armor. But depending on your perspective, this is actually a really good rhinoceros. For someone who has never seen a rhinoceros before, this is pretty on point. So it comes down to, what is the decision context that we're in? What are the decisions that we're trying to make? Because this is a much closer rhinoceros than a rhinoceros beetle, right? And this is a much closer rhinoceros than something else that also has a horn that looks kind of like a rhinoceros, right? So depending on your context and what you want to do, whether you're at the screening stages or whether you're at other stages, it all depends on how close to that rhinoceros you have to be. I would argue that if we were in the clinic providing some sort of tool for an intervention, we want the rhinoceros to look like a rhinoceros, right? As close as we possibly could get from a risk-benefit ratio, we want it to look like a rhinoceros. But if we're early in trying to understand this from a screening perspective, maybe even getting the fact that it has a horn drives us in the right direction for future work. So I guess I'd have us all think about what the tools are and what the applications are, and think about it from that perspective. So to go over what we learned in the last day and a half, we learned about genome editing, including CRISPR-Cas systems, repressor activators, epigenetic modifiers. We heard a little bit about fluorescent protein and genomic imaging, but there's a lot more there. And from the session one, which was really the level setting for all of us, we heard about the toolbox of genome editing is largely nucleus agnostic. So that has helped it accelerate as quickly as it has, and that also provides the opportunity as new nucleases, those that provide more specificity perhaps, can also just leapfrog one another. We heard that zinc finger and CRISPR-Cas9 are engineerable to clinical grade nuclease specificity, and that was a quote from Vikram Patanak. We heard that Cas9 does have off-target effects, but at a level tolerable for most research applications, which is why I put the rhinoceros picture in there, because I think tolerable for most research applications all depends on your context, what you want to do, and how you interpret your data. We learned that engineered Cas9 variants can provide no detectable off-target effects, and that's a really unsatisfying phrase to me, but that is what we learned, right? So is proving that negative really enough? How much is enough, and how do we learn more about that? One thing that I think was a great add to this was the concept of leveraging the extant genomes. So the concept of using the different mouse strains, taking what we know already and building a diverse population and providing data around that. That was really exciting, and I want us not to lose that as we think about genome editing. And we learned about inhibition and activation, CRISPRs, and we learned about tox-CRISPR and the use of that as a screening tool, which I think is very exciting and a very nice complement to transcriptomics and other approaches that one can take. So what Gary Miller showed us this morning is then taking it from what it is to how we apply it within environmental health research. So is environmental health research special? And I think these are three really important questions that take the tool and technology and has that rubber meet the road with regards to our environmental health research. So is it really any different? How can we get guidance, and NIH provide those guidance on gene editing used by the grantees? And having that transparency, promoting the reagents, who is going to have the warehouse of the best cell line with this particular change, and how do we have the data transparency in that step? So then for session 2, we heard a lot of different case studies. And I know we all wanted to hear a lot more from each one of these people, but we had the opportunity to cast a wide net and hear the waterfront of lots of opportunities, lots of really exciting ways in which these tools are used. We heard about piRNA and interventions and concepts around there, genome CRISPR screens, stress responses, translational opportunities, single gene knockouts. We heard about non-mammalian species, which I was really excited about too, because that is a huge advantage of some of the newer nuclease technologies versus some older technologies, and our ability to understand environmental health as it's not just rats and mice, because it's a very humanocentric perspective, was really exciting. We also learned about complexities, complex etiologies like rat metabolic syndrome, which was fascinating. Of course, with each one of these opportunities, it's science, so they all have their own sets of challenges and plenty left to figure out. A big one is knockouts often are different from knockdown, and we've known that for a long time in different types of genome editing things, and understanding why, and if we can use the tools to understand why and what does that mean, that's important. One thing that was clearly raised is challenges in delivery systems. Right? So the delivery system that you are using may be somewhat easier in vitro as long as you can get a high transfection efficiency, but how can that really be utilized in vivo, as well as the timing of that to that animal, if that animal is an adult or juvenile, or how do you do this in utero, the dosage that you actually use, the transfection efficiency or infection efficiency, depending on what model you're using. We talked about mitochondria, a really key organelle within the cell, yet we can't really use these same genome editing techniques for mitochondria because of getting it into there. We talked about low expressing regions of the genome where you would not be able to use some of these tools for lower expressing regions. And again, back to the classic relevant in vitro cell model. So it's easy to do in cells that are probably further away from cells that are relevant for our research, and work to do in that space. So you could see that as a glass half empty, but you could also see it as a lot of opportunity and a lot of things that we have to still figure out and left to do. And then for session 3 today, it was about lots of things that we can do and what it means. And that's really where the rubber all meets the road. So if we go back to the goals for 28 hours ago, I think we did a pretty good job actually of achieving these goals. And thanks to the wonderful speakers who gave us a nice breadth of exposure to these. I think it was particularly successful. What I want to leave you with, though, with where we go from here, in addition to the write-ups that we're going to have and all the great research we're going to do and the RFAs that will hopefully come from all of this, is a concept that David Gorhold put up yesterday at the end of the day. This is a great slide because it helps you look at, okay, you have all of the tools at your disposal now. You have tools that you were never able to have before. You have models that you can use with those tools, and then you have goals, questions that you want to answer on the other side. So I'm thinking of actually printing this out and connecting the lines and connecting the dots to figure out what are the possibilities, what are the opportunities there. And I guess I would start with all the way on the right-hand side, because it seems to me every time you turn around, there's a new technology or a new model or a new tool. It's almost like open sky thinking, right? Because if you can think about something that you want to do, chances are there's someone who is working on a tool to help you do that. I mean, that is the area of science, that's the time of science that we're in right now, which is incredibly exciting and hopefully can help us advance our science really well. So I'm gonna do this, but I'm gonna start all the way at the right with goals and then work my way back over. So that is what I wanted to share with you today with genome editing. I think the future is really, really bright. And as an optimistic scientist, I think we actually have an opportunity to take this tool as well as many of the other tools that we have in our disposal and really make a difference with regards to human health, public health. And I thank you for your time and attention and all of the great engagement over the past 28 hours. So thank you very much.